Let's take a look at our type 1 and type 2 errors. And what we're going to do to start this is to come up with the American theoretical system of justice as our precursor. So what can happen? The truth is the defendant is innocent or the defendant is guilty. Similarly, the decision of the court will either acquit or convict. So if you acquit an innocent person, that's good. That's 1 minus beta. That's called the power. If you acquit a guilty person, that's bad. That's your type 2 error, called beta. If you convict an innocent person, that is also bad. That is your type 1 error. That is alpha. And finally, if you convict a guilty person, that's good. That's your 1 minus alpha. All right, so using this logic, it is worse to convict an innocent defendant than to acquit a guilty defendant. So using this kind of structure, we, as the researchers, want to control the type 1 error alpha. So that's also known as the significance level. So let's apply this to statistical tests. Again, if the truth, the HO is true, HO is false, and then your decision, you will fail to reject HO or you will reject HO. All right, some people say except. I fall into the camp that is fail to reject. It's the same thing. So if I fail to reject a true null hypothesis, that's good. Again, that's your 1 minus beta, that's your power. If I fail to reject HO, when in fact HO is false, that's bad. That's your type 2, that's your beta. If you reject HO when in fact it is true, again, that's bad. That's your type 1 or your alpha. And finally, if you reject HO when HO is false, that's good. That's your 1 minus alpha. So if you want to put this in terms of a probability statement, you will say the probability of rejecting HO, given that HO is true, there's your probability of the type 1 error, there's your alpha. The probability that you fail to reject HO when HO is false, that's the probability of the type 2 error, beta. So let's go back to the actual question. Rejecting the null hypothesis when in fact the null hypothesis is, rejecting the null hypothesis when the research hypothesis is false is A, the effect size, B, power, C, type 1 error, D, type 2 error. Okay, so if the research hypothesis is false, then the null hypothesis is true. So this is saying, what is the probability of rejecting the null hypothesis when in fact that is true? That is your C, that is your type 1 error, that's your alpha, that's what we want to control. The second question, failing to reject the null hypothesis when the research hypothesis is true is effect size, power. Let's switch to the next page. Type 1 error and type 2 error. Okay. So here we have a true research hypothesis, which implies that the null hypothesis is false. When we fail to reject that null hypothesis, when that null hypothesis is false, that is your type 2 error, that is your D. All right, now, question C, setting the significance level at alpha equal 0.10 instead of 0.05 increases the likelihood of type 1 error, type 2 error, failing to reject the null, and accepting the null hypothesis, in fact, when it is false. Okay, so as we have mentioned, we, the researchers, control the significance level. People will ask, why don't we just set alpha equal to 0? But that's an interesting question. So the relationship between alpha and beta is complicated, almost like a teeter-totter, if you want to think of it like that. So if I push alpha down to the bottom, that's going to push beta very high. So in this one, I'm increasing alpha, which means I'm decreasing beta, which means I am excuse me, I'm sorry, I increased alpha, which decreased beta, and actually is increasing the power. So if I set that alpha equal to 0.1, the beta will be smaller. The answer doesn't appear to be in the set. What you really want to do is say on that one, you are increasing the power or decreasing the type 2. Thanks.